When you speak into a microphone, physical sound waves turn into an electrical signal. But when you listen to a loudspeaker, the exact opposite happens. It takes an incoming electrical signal and turns it back into physical sound waves. In engineering, any device that converts one form of energy into another is called a transducer. It operates on the simple principle of transduction. We divide transducers into two main categories based on the direction of that energy conversion. Devices like the microphone are sensors. They respond to a physical quantity and output an electrical signal. Devices like the loudspeaker are actuators. They take a signal and respond with physical movement. Modern measurement systems rely entirely on converting physical reality, like temperature, pressure, or flow, into readable data. Because of this, selecting the correct sensor from thousands of available options is the most critical step in designing a reliable measurement system. To monitor this heavy industrial engine, we need a temperature sensor at this specific attachment point. How do we find the right hardware? First, sensitivity. If temperature increases by 1 degree, a low-quality sensor misses the shift completely. A sensitive transducer outputs a clear, readable spike. We need this high sensitivity to extract meaningful data. If the physical changes in the environment are minute, a sensor with low sensitivity will output a flat line, making it impossible to tell if the engine is running steady or slowly overheating. The second rule is checking the electrical output characteristics. The sensor's specific output parameters, its impedance, frequency response, and response time, must perfectly match the inputs of your recording device. A highly sensitive sensor is completely useless if its electrical language is incompatible with the rest of the measurement hardware. The incoming signal simply will not record. Our third rule evaluates the physical environment. The sensor must survive hazards like intense vibrations, constant moisture, and extreme ambient heat. Even if the sensor is otherwise perfect, rising afternoon heat can make its data line noisy and erratic. Ambient heat interferes with the readings. How do we fix this error? Pause the video and see if you can identify 3 techniques to reduce environmental errors before the system fails. Fourth rule, error management. Technique 1 is calibrating the transducer's output against a known standard to keep data honest. Technique 2 is continuous monitoring. A secondary sensor tracks ambient heat to mathematically correct primary readings. Technique 3 physically encloses the transducer in a temperature-controlled housing. The perfect, error-free sensor does not exist. Reliable engineering means anticipating these environmental limitations and actively designing management systems to control them. Let's apply this logic to a completely different measurement scenario. This diagram illustrates a system for measuring the physical weight of traffic on a bridge using a strain gauge connected to a Wheatstone bridge circuit. The strain gauge acts as the sensor, detecting the physical deformation of the bridge and converting it into a tiny electrical change. The Wheatstone bridge serves as the signal conditioning unit. Working together, this combination functions as the complete transducer unit. Whether you are measuring the internal heat of an engine block or the structural stress of a highway bridge, hardware selection relies on the exact same 4-step criteria. Here's the summary checklist for your future designs. First, define the exact energy conversion required. Second, verify the sensitivity is high enough to capture your smallest input changes. Third, guarantee the electrical output matches your recording hardware. Fourth, ensure the sensor can survive its physical environment. And fifth, implement active error control techniques to manage the hazards it faces. By defining the required energy conversion and methodically applying this selection criteria, you eliminate guesswork and guarantee accurate data collection in any environment.